everyone, and thanks for having me with the department. So today I'm going to talk about some basic machinery of how systems as wiring diagram algebras can be perceived. But of course I'm going to give essence to everything, I guess. Wiring diagram algebras. This is supposed to be vague on purpose, in a sense. So I'm going to go through some basic pieces of methodology that basically David Spivak, but also other collaborators have been developing over the last few years. And I will take things very slow. So definitely if you have any questions, you should ask me. And this is supposed to be really introductory. So I don't know if I'm going to go into the most abstract machines that we defined in our latest reference, but we'll see how this goes. Okay? So the motivation, if there's any broad motivation picture you should have in your mind, is that there's a bunch of systems in a broad sense or in a more specific sense. And this formalism, this wiring diagram algebras formalism, is providing a very robust framework for how to perceive pictures like that, like axiomatize exactly what's going on when you want to do some things with systems and arbitrary compositions of them. So everything is going to become precise in a second. But the general idea is that, for example, recently I was looking at I'm going to be talking about finite state machines a lot today, and I was looking at the references of how people compose them, like Moore machines. And indeed, there are specific ways of writing down formulas for composing them in parallel or serially, but it looked to me as if every time somebody would have to come up with a new way of combining them and making this precise. But this framework, first of all, it doesn't only work for a specific kind of system, as we're going to see, but it gives you a way every time you want to make an arbitrary wiring interconnection there to give an essence to that, a mathematical essence via formulas and the rest. So the idea, very broadly, is this: give essence to how those things interconnect and how you can talk algebraically about them. Another goal that we had at our common project with David and Patrick was that we wanted systems of different types to talk to one another. So usually this could be, if these were all state machines, then the composite system would also be a state machines. But what we wanted to do within this NASA project that we had some years ago was to be able to connect different kinds of systems, yet be able to talk about their composite in a general enough framework. So this is some very broad motivation of different things over the years that have passed, but I really want to get to the gist of what's going on. So I'm going to start from the beginning by describing exactly the category. So WC, the symmetric, monoidal category of C-label boxes and wiring diagrams. So what is that supposed to mean already is those two pieces of names I put on the board. These are going to be the objects and they're going to be the morphisms. So really the wiring diagrams are going to be the morphisms in this category. So fix some C, and this is going to be set for us for the most of this talk, to be a finitely complete category. In fact, if I wanted to be more precise, only products are enough for most of what's going to happen today, but it's good to have finitely complete categories for later when this come together with a more abstract formalism. But anyway, let me just say here that, especially for this definition, finite products are enough. It's just a bit easier to keep a little bit more general. So first things first, we need the objects. Okay? And the objects are easy enough. They're just pairs, x1 and x2. So an object x is really a pair of two objects in C cross C. Okay? I'm going to try, I don't already have enough space, but I was going to try and have a visualization board here. So I'm going to first give the very general definition that could mean anything or nothing, but there's a specific way, visualization, that I'm thinking of them. but it's not necessary for the category as category. Anybody can get a bunch of objects and arrows and prove that something is a category at the end of the day. But there's a specific way in which I want to view this. Okay, the objects are just pairs. Now morphisms are also pairs, okay, so let me just write phi from x to y are pairs of morphisms in C. Okay, as follows. Morphisms in C. Okay, so we have a pair of morphisms in C, and I'm going to write down that may or may not have any meaning for you. So phi2, I'm going to start for phi2 because it's easier sometimes to think about what's happening, goes from x2 to y2. So remember, this is x1, x2, and this is y1, y2. Alrighty, and then phi1 is going to go from y1 times x2 all the way to x1. Okay? So this is a pair of functions which could be there for a reason, could be there not for a reason. I'm going to write down the composition and the identity, but before I go on, I wanted to say that this recently in the ACT meeting in Leiden, we realized that just this definition that has nothing to do with boxes, with wires, with whatever, you can see this is really abstract, okay, is related in a specific way which we still have to find to identify better. Dialectica categories, it's very related to dialectica categories. And also, this specific description of things is also very related to compositional game theory. So I'm just throwing some names here to make this sound a bit cooler. It's really cool. I mean, it is really cool that this abstract definition appears in so many diverse settings anyway. Compositional game theory. And also, this is relevant to bilenses, which is something to do with databases. Just this formalization of things, okay? So different semantics, I guess. But for us here today, there's a specific visualization for objects and morphisms that I would like to now show to you. So, okay, an object is a pair of objects in some category C. But really, I'm already thinking of an empty box, if you want to view it that way, X. And X1 for us shows the input ports, in a sense, and X2 the output ports, okay? So this is just like a way of thinking about this if you want to. And now, this have a specific meaning in this visualization process. By the way, that's what's called a C-label box. That's where the name of this category. Okay, and now the wiring diagram, which is a morphism in this category, could look like this. So I have an X inside, so instead of going from this to something else, this is really an inside-out process. This is a nested process idea that's happening from X inside to Y outside. So if I have X1 and I have X2, well, just do something first. So let me again start from the second part. This says that there is some function, this is some morphism in C, or you can think of it as a function in Z, that goes from X2 to Y2. So the X2 is really starting here, and the Y2 is all the way out here. So what I would like to think of, thinking about these wiring diagrams, is the flow of information. This is really the flow of info for us. So the inside box is going to feed like its output, that's going to be an output real soon, to the outside box in that way. So that's what this phi2 is really doing. And now what about this phi1? This has to do something with the input of the inside box and the outside box. So this tells me, if you want to see what kind of information the inside box gets, you have to look not only at the information from the outside world, but also you can feed back information from your own self. Okay? So this says X1 really can take information from X2 times Y1. And that is why feedback as an idea is really central in this formalization, even more than other things like serial composition, which I'm going to talk about in a little bit. So this is the visual way that I am thinking, and maybe you should be thinking for today, about these two maps. The flow of information, and this is called, so this is the C-label box, and here I have the wiring diagram. All right? So now I'm going to write down the composition and the identity just as a sanity check to see that everything works in the way that maybe we're expecting. I'm not going to prove associativity. So let me just write composition. I have, yeah, composition that goes as follows. We go from X to Y to Z, and you're using some phi and some C for your wiring diagrams, and not phi and psi. Okay, so what's really happening here is a nesting of 3 diagrams. Okay, because this is a zoom in, zoom out situation. It's really helping to view things that way. And what I said is that the wiring diagram, well, the function really, so the morphism really does something like this. Again, I said I'm going to make those precise for specific examples, but also this is supposed to also be able to feed things back to itself and then go to the outside world. And this is all directed. I mean, it is the flow of information we're thinking about. Okay? So that's what I'm trying to describe here. So the composition is, and let me just rewrite this to be very clear. Phi2 goes from x2 to y2, and C2 goes from y2 to z2. But then on the inputs, I have y1 times x2 that can feed my, phi1, feed my input here. And then I have C1 going from Z1 times Y2 to Y1. Okay, and now I better find something that goes from X to Z. So for something to go from X to Z, it needs to start from X2 and go all the way to Z2, to the outside world. So this is kind of self-explanatory, maybe, maybe not. So you first need to go out to the Y output there, and then you have a way of going all the way out to the Z output. Okay? So now it's the more elaborate part, because at least you can see the row of information going that way, and we're using the specific maps to do that. But let's start from the beginning. I better start from Z1, because that's where I'm mapping out in here, okay, times X1. Because I'm really composing these morphisms to go from X directly to Z. And I better end up in X1. Okay, that's how my composite is going to look.
Did you mean X2?
I meant X2 exactly. That's paying attention. Okay, so let's see how we can do that. Okay, so as is very usual in category theory, well, this is like the reasonable thing for us to do, but let's see whether it makes sense, and let me make sure I'm not making any mistakes. I'm already seeing that this X2 output is using a few more times than I'm used to. So what I'm going to do first is 1 times delta. And remember, this delta exists because my C has finite products. So this diagonal map always exists. Or you can keep thinking about sets. That's absolutely fine. X2 times X2. So that's great as a first step. But then I see that by combining something, by actually going from X2 outside to the Y2, I may be able to use Y2 with my Z1 to actually go inside. So that's what I'm going to do. I'm going to apply phi2 there and go Z1 to Y2 times X2. I need more space, clearly. So that's great because now I have a way of doing something here. So this will take me via the map C1 times 1 all the way to Y1 times X2, and then bingo. I have a way of actually inserting my box X. So in a sense, this is the reasonable thing to do. It uses all the pieces of information, and it's associative and unital. Let me just also write down the unit. Sorry, the identity, to use notable categories. Okay, so the identity should go from the box to its own self right here. And then again, it's kind of what you're expecting this to do. So X2 will go to X2 by the identity function here. And then somehow you can like feed yourself back to yourself, but because this is going to act like an identity, you don't really want to take notice of that. So you're just going to forget that you could always like look back, and this is projection.
So X2 times X1? Yeah. Right.
Thank you. Exactly. Okay, so that's what's going on over here, and everybody's happy already. And now we want to check, we won't check, but you can check this is associative.
I think it's X1 times X2, sorry.
Oh, yeah. The x2 we forget, we keep the information of x1. That's absolutely right. Associative and unital. Okay, and then we want to see exactly what the symmetric monoidal structure is, and that's it with this category. That's going to encompass a lot in this formalization. Okay, so that is the categorical structure, and I really don't want to go over there, so let me just say here, monoidal structure is given by parallel placement of boxes, and that's why parallel placement of boxes is so important in formalization, but also in general. So let's have x and z, or y. Why would we change? Everybody knows. So we want to put them in parallel. So suppose we want to take the tensor product in this monoidal category I'm defining. This is exactly going to be x1 times y1, and then x2 times y2. That's why products are so important. You can just do this as a new box, like this. Okay? So this is what the monoidal structure is doing, and then let me just write the unit. Because you see, the tensor product is using heavily the product, so you would expect the unit to be just 1. You want 1 times whatever, give you the same unit. Okay, so that is the general description of this category. That is the general description of this category. Okay, and then I just want to give some intuition and then do a couple of examples in set, just to get us started. So the intuition, if there's any, like, this is better than what I've been doing, there's like physical, or like examples that I'm going to do now in a little bit. So the physical boxes, if that's what we're going to call it, they're not really physical, look like a box. It can have many ports, okay? It can have many ports, and I've been drawing them as one port, but what I just want to say is that that's not important, because so I'm going to call them A1 and AN, so finite number of ports here, B1, BM here, where so these are just a collection of ports. There's nothing attached to them yet, where each AI and BJ are associated, they are associated with an object, with their type really, with an object. So we write this as tau for type, I guess, I don't know, in C. Okay? So that's why C is sometimes called the typing category, because that's what it's supposed to do. You can have a bunch of wires here, and then you have the typing category that tells you what sort of information passes through that, the type of info that passes through, and really in this formalization passes through, what we're doing to view them as C-labeled boxes is that we view this box as having x1 and x2, just the products of all those types. That's what's really happening. So usually in many of the previous of David's paper, also in our paper, we start by describing a little bit different of a category there, and then we're taking the products and we end up in this category. But this period, I'm convinced that this is very central because it also comes together with everything else. And this intermediate step is really just for the sake of bringing everything together. So I think this description might be more central than the usual wiring diagram category that has sets of inputs and things like that. But that's really, I didn't hide anything. That's exactly what's going on. Okay, so that's here. So everything is in C, and that's why you need C to have finite products. So let me do an example of a wiring diagram in WC. Example of 2 wiring diagrams. And I just wanted to notice in W set, that this, we're already talking about empty boxes. There are no semantics attached to any of it yet. Still, you can do a lot of stuff. You can describe a lot of arrangements without having given any meaning to them yet. So even at this stage, this is quite powerful, that like any, well not any, but most things that we care, the ones I've seen, any wiring arrangement can be expressed using this phi. just some phi. You can define this phi to express your wiring diagram if you want. Can be expressed using some phi, some wiring diagram phi. Okay? So let me do the first one. Suppose I have a box here, a W set, a labeled box in set, and suppose I know that its input ports, there are 3 input ports here, and this has information of the set A, like elements of the set A, elements of the set B, and elements of the set C. So really, x1 is A times B times C, exactly as I said before. What's supposed to happen here? And suppose we have output A and D. So x2 is A times D. They're all sets. They could be 0, 1, truth values, integers, whatever you want. And then suppose I want to form the following wiring diagram, because I can. I mean, I will just do this. I will make this have a feedback loop if I want to, because they have the same type, of course. Otherwise, I wouldn't be able to connect them. And then I want to say, okay, I'm going to take this output and put it on the outside world like this. I can duplicate. This is the forking. Okay, and then the input will be this. So B, C, and I could have another input that completely like disappears on me, but that's fine. So I can form this wiring diagram. And by form, I don't mean just draw the picture, which is very beautiful as you can see, but I can also write down phi, okay? So for the specific thing I drew, let us just write phi and see how easy this is. So for the output 1, I'm supposed to go from D, I'm not supposed to go from D, sorry, I have 2 output wires here. I'm supposed to go from A times D all the way to D times D. But what this is supposed to do, physically and really, is forgetting that you ever had an A, for the output at least. You don't need that anywhere. So this is P2, and then you just duplicate. Okay? So this is the output like wiring part that tells you what happens for the outside world. And what happens to the inside world? Well, based on the general description, I need to start from y1 times x2 and end up on x1. So what is my y1 here? My y1 is this, and that product is. So B times C times Z. So this is my y1. Products are always nice. And then with the output of x2, which is A times D, which is x2. And I need to go somehow to the input of x1, which is just A times B times C. Well, you just make this function do what you want it to do. Like take B to B, take C to C, forget about E, and forget about D. So there's always a way to do that. B, C, E, little elements because I'm working in set now and then map it to A, B, and C. This is some sort of projection. So that's what I was trying to convey earlier, that for any, sorry?
No, you said oh.
Oh. Like if you want to draw something, you can give this meaning to the wiring arrangement just by writing down a pair of functions like this, okay? So let me do another example which is fundamental, because as I kind of said earlier, if you look at the basic structure of this category, like you have the box, you have the feedback built in the morphism, and you have the parallel placement built in the monoidal structure. What we don't have, which is very, very common in systems and the sort, and in categories, by the way, is serial composition. There is nothing around that I can use for serial composition yet. But let's just see that there is a specific wiring diagram that will give me the way using these basic blocks to build a serial composition. Okay, so another example of wiring diagram. Well, this example may be 1. This is just some wiring diagram. And this is specifically a wiring diagram that gives what we expect of serial composition. And that's something, a very subtle point here that has to do with operands that I haven't talked about, and I'm not going to talk for a specific reason, but I will mention something at this stage. Okay, so suppose we want to write down, the wiring diagram that makes this possible. Okay, so this is X, this is Y, and this is Z on the outside, the composite of the two. And here we have some set A, some set B, and some set C. And I want to be able to write down a phi that completely makes this possible. But this is a monoidal category, okay? So what I'm trying to say is that this picture, and all the pictures usually of wiring diagrams, happen in the underlying operand of a specific Okay, so what I'm trying to say is that pictures, usual pictures like the one I just erased, are really happening, like formed, happening in the underlying operand. And the underlying operand for any monoidal category says that you can have a map with many inputs and one output as long, so this is a map x tensor, no, well it's not, sorry, x comma y to z. This is an operatic way of thinking, but in my monoidal category, because this is the underlying operand, this is really a map like this. So whenever people, or me, or whoever draws a picture like this, what's really going on is that you have to shift your perspective a little bit and view this as follows. You need to view this as a morphism from the parallel composition to the outside thing. Okay, but of course we can do that because those wires are just like, sorry?
I said,
Oh, words. These diagrams are really like flexible, so flexible. This is B, this is C, and this is just A. So, I hope you agree with me that these are equivalent as pictures. Well, I'm sorry for that. I wanted it to go the other way, but it doesn't really matter. I destroyed everything. Okay, so it's like this, and it goes from the composite to the thing. And let's write down exactly the wiring diagram that makes this work. Okay, so let me just refresh your memory. X times y is really y1 times y, x1 times y1, x2 times y2, and then y, sorry.
X1 times.
Yes, but what I wanted to do actually is just say that there are specific sets here, so I can make this more precise. Okay, so x times y is just, the input of it is A cross B, and the output of this is B cross C. Okay, so I'm going to write down a wiring diagram that actually encompasses this information as a phi going from x times y to z. So for the output function, which is always the easiest, I think, so phi2 should go from the output of this box to the outside world. So the output is just B times C going to the outside world C, which is just P2, pi2, projection. Okay? Now what's happening in the input is the following. So first of all, I need the input of y, which is A, sorry, the input of z, which is A, and then I need the output of the box that's happening inside, the composite box here, which is B times C. And I need to somehow produce an A. Sorry, produce an A times B. This is the input here. Okay, the input of this. And again, it's happening what we were expecting this to do. P1, 2. C just leaves to the outside world, not making anything happening in the input, but then A and B, like B is fed back, but A is coming from the outside world playing the role. So this is the serial composition written in the world of wiring diagrams, even if this is not like a building block of everything else that we've talked so far. Okay? So these are two important examples. Well, the second one is more important. And then let me just say something more high level and then go give specific examples and start talking about algebras. As I said, these are all empty boxes. These are all empty arrangements. It gives you a language, but it doesn't have anything that it applies to. It gives you a way of talking about this. It's very expressive, but it doesn't have a meaning yet. Okay? So what I wanted to say is that, in fact, there's no way I'm using different kinds of things every time. But anyway, that there is a functor. Okay, so W blank. I didn't talk about the maps at all, but you expect this to be high power. It's very categorical already. That goes from finitely complete categories or finitely product categories, but for what comes next, this is more useful, to symmetric monoidal categories. And it maps every typing category, all these categories that you can have that say what possible information goes through them, to WC. And there is a way which I'm going to briefly describe here. If you have a finite product preserving or finite limit preserving factor from C to D, goes to WD here, and there is a strong monoidal, symmetric strong monoidal functor that goes between them. And that's what this category is supposed to be, symmetric mon cats and strong mon functors. All right, so this is what's going on. This is W sub K, and let me describe this real quick. So this says where each label box X, X1, X2 really gets mapped to just KX1 and KX2, which is what you expect, just changing the types of the wires in a sense, and some phi like this, like before. So this is phi2 and phi1, like I wrote it before, gets mapped to something that is like K applied to this, but in a specific way. So there is a K phi2 that goes from KX2 to KY2, all right? But then on the input side, I have KY1 times KX2, which is supposed to be my new input thing going here, but then you need to use that K-preserved products to actually land on Y1 times X2, and then be able to apply K to phi1 and go all the way to KX1, okay? So this is how this functor works, and let me just say that this is really changing the typing category, changing the types of the wires, in a sense that makes sense with everything else, okay? So let's keep going. We've talked about this wiring diagram category a lot, but what we haven't talked about is the semantics of all this, like language, like how is it really going to be used to model real situations. And this semantics, this kind of viewing things with meaning, is going to be for us just a lax monoidal functor. So a lax monoidal functor from this category all the way down to cat or set, to make it a bit more simple maybe, is really what make those boxes not be empty anymore, but have something inside of them that actually acts and does something. So semantics. Okay, so let's see what a lax monoidal functor does, and let's convince ourselves that this is what actually fills the box with something. A lax monoidal functor from WC times I, where we described it earlier, all the way to cat times 1, okay, takes empty boxes, well, takes boxes, you can just say empty to be dramatic, okay, so let me just take a picture here. I'm going to do stuff to this picture. So I have X, I have Z, I have Y, like somehow from the beginning, this fits that, this goes out, like that's a wiring diagram arrangement, which we can write using those fits down.
What does that say in the third compartment of the second triple?
That's the identity.
The identity category, this is the unit category.
Okay.
Yeah, this is the Cartesian, the usual Cartesian project on cat as a monoidal category. It's a terminal category, one object, identity marks. Okay, so it takes empty boxes and chooses, well, assigns, just say assigns, a category or a set of inhabitants. That's how we call it sometimes. Inhabitants. Inhabitants for each. It populates them in a specific sense. Okay? And that's the mapping on objects. So what this does is taking X, X1, X2, all the way to some category, so let me call this F, okay, to F of X, which is all the things that can be there, all things that live there. No, this is being very free in a sense. Let me just make it more precise. And then, given a wiring arrangement, like over there, a wiring arrangement, I want you to see exactly how, using the data of a lax monoidal functor, we can take this box, we're going to inhabit it now with a category of things that can live in. One thing, but let's just say a category of things that can live in. And given a wiring arrangement, I will perform the following thing. So first of all, as we did earlier, I'm going to view this in the monoidal category because I have no way of understanding this. So f of x is going to be here, f of y is going to be here. Then for the specific reason, well, f of z can be here. Then you have this, you have this, you have this going outside, okay? And you see already that I'm forming something here. So I start from f of x times f of y times f of z. So I'm choosing an F system, a system of type A, of algebra A. This is the algebras, sorry. That's what we call an algebra, a lax monoidal functor. Okay, so take a system that lives, take a thing that lives in here, take a thing that lives in here, take a thing that lives in here. First of all, apply the laxator, phi 0, called the lax monoidal structure. Take the laxator fxy and have f of x, y, z. So what happened here is that I took one thing in here, one thing in here, and one thing in here, and I transformed it into a thing that lives inside the composite here, the monoidal tensor product. Okay? So this is phi of x, y, z of A, B, C. It's really the one inhabitant of their tensor product. And then, the most important part perhaps, is that this f applies on objects but also applies on morphisms. And this is going to be f of, oh my god, I'm sorry. Let me just change my letters here real quick, because I want to have a specific wiring diagram here, which I'm calling phi from earlier. Okay, so there is a phi here, and then my lax monoidal functor take this phi and says, given three things, well, one thing on the composite, I'm always going to give you a functorial way to write a system on the outside box. That's what f of phi is doing. It's going from this to f of y. This is really where the composition of system is going to happen. Given three of them, we're going to take a new one that lives on the wiring arrangement of them, on the composite of them. So this is the one inhabitant, a specific inhabitant on the outside box. And that's really what we call, well, what should be called composition. So taking any...
But phi x, y, z is now
Yeah, sorry.
f, x, y.
Yeah, thank you. Yeah, it's changed. Yes. So, given three F systems, so three systems that convey, that have to do with a specific algebra, I'm going to do an example right away. Then, for any wiring arrangement of them, in the sense that we were talking about earlier, you can write down the phi. We can give a specific description on the system on the outside box. And let me just say that all these are happening for a specific algebra, for specific F. This means that if all of them are discrete dynamical systems, continued dynamical systems, other sorts of weird state machines, the outside inhabitant is going to have the same description. It's going to be given by the same amount of data, but constructed from the three things I gave here. Okay? So, if all this for specific F, okay, I think I shouldn't write anymore, and I should just try and make this a bit more precise. And last comment I wanted to make here, yet another symbol, okay, is that in recent terminology and based on some work that me and Joe are doing with the monoidal index categories and the sort, I just wanted to say that every algebra is a monoidal op-index category. That's this way of writing things to sound a bit funnier or more like high-level things. So if somebody comes to you and say, oh, I just have a monoidal op-index category, you have no idea what they're talking about. But really what's happening is that this is a lax monoidal functor into cat with the usual tensor product. Okay? So if we want, we can have a category, and let me just write the category, that WC algebras, which is the collection of all monoidal functors from WC to CAT, and monoidal natural transformations. I don't think I'm going to have time to talk about maps between systems, but this is precisely mon, cat, L, lax monoidal functors from WC all the way to CAT. So it's really things that are widely used and understood, things like that. Okay, so without further ado, let's make sense of these algebras. Let's see examples of these algebras. I'm going to focus on the state machine algebras, the Moore machines really, and see how this language is allowing us to have a uniform way of composing them, for starters at least. Okay, example, very basic example, okay, of a W set algebra. Oops. Is discrete dynamical systems. That's one way of talking about those things. I'm going to describe them, but they're also Moore machines with an initial state, or these are more generally called FSM, finite state machines. Well, Moore machines, mini machines, and other things. The Moore machines are the ones that correspond to the discrete dynamical system. So, let us give the definition. Okay, x1, x2, and we're already like targeting back to our boxes. We just want to make things a little bit easier. Discrete dynamical system is given by the following data. Is a set S and two functions, f update, f read out. Okay, where S is the set of states. And then we have the two functions doing something. Okay, so we have the f update taking something from S and something from the outside world as an input and gives a new state S, and f read out takes something from S and produces something in the outside world for us to see as it output. Okay, so this is the update function and this is the read out function. Okay, so what we want to do is to denote, this is the collection of all things. It is a category, but I'm going to focus on sets to keep things simple. Denote by D, D, S, X1, X2, the set or category really, I don't want to talk about morphism now, or category of all those systems, okay? Of all X1, X2 discrete dynamical systems. Okay, so we are going to give a description of an algebra and see how this machinery is going to allow us to interconnect arbitrary of those. We're going to make a couple of examples. Maybe that should be the end for today. Define a W set algebra as follows. Let me write the image, the mapping on objects. So DS goes from W set to cat, as we said it would. Okay, and the mapping on objects is very easy. Taking every empty box with input and output in set, and it gives us just the collection of all the discrete dynamical systems you can put in there. Okay, that's where this definition was building. Every one of those boxes is going to have one guy, set of states, update function, and readout functions inside of them. Okay, and let me now say what this does on a wiring diagram for phi from X to Y, which is really, as I said earlier, where the composition is taking place. I have a system in here, and I want to produce a system in D, D, S, Y1, Y2. Okay, and let's see exactly how this algebra works. How does this algebra, given a guy on an inside box, produces a guy on the outside box? I'm going to keep this because I'm going to use it for an example. So now, given those two functions I wrote before, so from s to x2 and from x1 times s all the way to s, and this is f update and this is f readout, and also a wiring diagram arrangement that goes from x2 to something else, y2, phi2, and here you have y1 times x2 goes to phi1 all the way to x1. So given those two things, I want to produce a new thing. We can define a y1, y2 system. Okay? So to provide a y1, y2 system, I need three things. I need the set of states, I need the update function, and I need the readout function for y1, y2. So first of all, it has the same set of states with the same set of states. And if only now we can write down what the new, so G or any name, or it's okay, the new update and readout functions are going to do. Once again, the readout function is kind of clear. So if I have a discrete dynamical system inside my box X, there is a bigger box Y, there's some sort of wiring like interarrangement here, then this is first of all going to output something out of X1, but then it's going to use my phi2 to go all the way to Y2. So the message really goes to the outside world using those two functions over there. But now let's see what happens for the new update function. So given a new input of y1 all the way out here, and a state here, how am I going to change the state? I need to reach S. And again, this is very similar to what we did before, is what is the reasonable thing to do? Okay? So first of all, I'm going to duplicate my state, because I can, I'm in set or in any finitely complete category. Okay? And then I'm going to first read out what I have right now, like what my current state does. I'm going to read out this and go from y1 all the way to x2 times s. And then I'm going to use phi1 to get somehow my wires all the way located to x1 times s. And then there's nothing left to do but use my usual update function and produce something in s. Okay? So again, this is like what you expect to happen by using all your information, but also kind of looking at this picture and imagining little states here moving out and inside. So this is how the algebra is functorial. Well, the assignment is functorial, but let me just show you the lax monoidal structure, and then we're going to do the example. The lax monoidal structure of this thing needs to start from something in x and something in y, and produce something in x times y. Okay, and this is basically just tensoring all the things you have, taking the products of all the things together. So the state here, if you have S and T, the state of two parallel dynamical systems like that is always the product of them, and that's classic. This is typical in those situations. And then having F update and F readout, well, we're using really the symmetry here at a certain point, but essentially is F update times G update, well, composed with a symmetry here, and then F readout times G readout. So this is really what you expect things to happen. If you put two things in parallel, they just work independently to one another. So now this is the lax monoidal functor that expresses the discrete dynamical systems, and let's see some examples finally to see what's supposed to happen with using this machinery in real-time examples, whether we can understand the examples follow from this framework in a reasonable sense. Okay, I'm going to introduce two discrete dynamical systems, two more machines, but they're pretty standard. Well, intuitively they make sense. I mean, it's something that we will understand, and then we're going to wire them together and see what they produce using this machinery we introduced. So, let's first of all describe the following system, okay? And the following system is somewhere on my papers, and it's lost here. Okay. So, suppose A is true or false, 0, 1. That's going to be basically my input and output wire just to keep things simple. The first system, so system number 1, I'm going to give it a name in a little bit, has 2 states. It has state A and state B. So x1 here, S for my first set of states is just AB. Now, if you notice the definition of discrete dynamical systems with IRAs, each state has an output right away. There is no interference with the input for every state to have an output. So I can right away tell you what the output is of each. And that's a very typical way of writing dynamical systems. A always points out to 0, and B always points out to 1. So far, so good? This is the output. This is F readout for my dynamical system. Okay? So this is my first state that reads 0 to the outside world, and this is my second state that produces 1 to the outside world. What's left for me to describe this dynamical system is the update function. So the update function says, given A.
What's x1 and x2?
Very good. x1 and x2 are A, which are just the truth values. So what I just wrote here is that S to x2, which is the readout function, maps A to 0 and B to 1. Just need to give a function that tells you what the states do. I only have 2 states, so that's easy to describe. Okay? And now I need to produce the update function. Okay? It can be anything you like. It can be any function you like. Let's just see something that actually makes some sort of sense. So if I am at state A, and I'm getting a 1 out of the outside world, I'd stay at A. So let me write it again as I had before. S times x1, x times A goes to S. So this little loop here says, that's how they write it, and it makes sense after a bit. If you take A, and if you take 1 from the outside world, then stay at A. Don't change your state, just stay at A. Okay? But then what happens if you feed it 0? Then that's going to go to B. And that's done by this little thing over there. So that gives you all the information without writing the functions every time. Okay? And let's see what happens to B. Well, B, whenever it gets a 0, it stays B. So this just says B0 now goes at B. But then if you give him a 1, it goes to A. So B1 goes to A. And that's really the whole description of the discrete dynamical system, the same way we were talking about them earlier. All right, so what do you think this machine does? Suppose I feed this machine the following series of inputs, okay? Have I chosen one? For a certain reason, I don't remember. So input, the string. So first 1, then 0, then 1, then 0, then 0. And let's see what happens out as an output, okay? So I start from A, because that's the initial state I chose. Okay, and then I'm going to do 1. Where do I go? I stay at A. If I do 0, I go to B. If I do 1, I stay at A. If I do 0, I go back to A. And if I do 0 again, I go to B.
Right.
Okay?
For B and we have 1, we go to A.
You're right. Very good. Excellent skills. No, you're right. So from A, 0 goes to A, and then 0 goes to B. Does this look correct?
0 should go to B.
It does go. You're right.
Even the first time. Now it is.
So, what does A output? 0. What does B output? 1.
Right, I see.
What does A output? 0. What does B output? 1. What does B output? 1. I'm not taking this into account because I need to start seeing outputs. Output happens 1 clock tick after the inputs. So this produces to the outside world this stream, which is 0, 1, 0, 1, 1. So this is the NOT machine. Cool. Okay, so this is the NOT machine. Okay, this is a simple discrete dynamical system that takes any input and produces the other one. Let's do another discrete machine and see whether we can see what it does in the same way of thinking, and then we're going to compose them. See whether we can see what the composite does. Okay, that's one example of a machine. I'm going to erase the things on the right so I have more space, maybe. Maybe. Okay. No, sorry, I want to start on top. Okay. I'm going to have three states. I'm going to have the states R, S, and T. So R, S, and T. Like before, I'm supposed to straight away give you their output, okay? So this is again an AA machine. AA Moore machine. Or discrete dynamical system, they're the same. Okay, so their output straight away, I'm going to give it to you is 0, then 1. Okay, again in the same format as before. This is one state, this is another state, this is the third state, and their outputs. Let's see what the input function does. Okay, and because I'm inputting 0 and 1, again like before, it's enough to just draw little arrows to tell you what they do. If I'm at R and I'm fed 0, I'm staying where I am. But if I'm fed 1, I'm going to S. If I am at S and I'm fed 0, I'm going back to R. But if I'm fed 1, I'm going to T. And if I am at T, if I'm fed 0, I'm going to go all the way to R. But if I'm fed 1, I'm going to stay where I am. Okay? So let's give an input to this machine and see whether we can see what it gives us. Okay? So for input 1, 0, 1, 1, say 0, okay, an initial state R. Let's do the following. Let's play R. So I need to do 1. R with 1 goes to S. With 0, it goes back to R. Oops. With 0, it goes back to R. With 1, it goes to S. With 1, it goes to T. And with 0, it goes back to R. That's what's happening for the states, okay? And let's now see the outputs of them. The output starting from clock tick here. So S outputs 0, R outputs 0, S outputs 0, T outputs 1, while R outputs 0. That's not as easy to see as the one before, but what's really happening here is that this machine is called the 1-1 detector. Whenever two ones pass the one next to each other, at the next step you're going to get an indication that two ones passed from this machine. Is this detector?
Would that be different if you started at S instead of Y?
Yes. So that's something I was trying to avoid to talk about. But the Moore machines need to be initialized. And there's another algebra of initialized machines, but I didn't want to go all the way there. Yeah, because if you start at S, then just feeding a 1 will output a 1. You see? If you start here, you don't need two 1s to produce a 1. So you better start here. Okay, so you're choosing your initial state. That's a good thing. Okay, so that's what's happening. And now I want to do two wiring diagram compositions. The parallel one, which is very simple, and then the serial one, and let's guess what it does. Okay? So the parallel composition, this is the NOT machine, and this is the 1-1 machine. Okay? And this takes input A and gives output A. This also gives input A and output A. And this is a very simple machine in the sense that these two things run nothing to do with one another. So you start feeding them now couples of zeros and ones. And one of the 0 1s will go here, one of them will go there. For example, they run in parallel. Of course. So e.g., if you start at initial state AR, remember all the states of the tensor product which are now erased are just products of the states. So AR is one of the states here, and then say I'm feeding it 0, 0. Then the output is going to be a new state. Well, 0 only affects A, so A goes to B. And R gets affected by the second 0, and R goes to, who knows, R. Okay, so they really run in parallel. But now we feed them pairs of zeros and ones, and they also will output pairs of zeros and ones as if they had nothing to do with one another. But now let's try and see what their their serial composition is doing. I think it's going to be the end. And as I said, some of the things, some of the composition, especially the serial one, which is very important, can be found written. But just because we try to keep things simple to show how this machinery works, doesn't mean that if you get an arbitrary wiring arrangement, you can play the same game. You can find an arbitrary number of machines and wire them together and say what the output does. It's not always easy to see just by thinking about this. You need to have a formalism to make those things work. So now, let's do oops, sorry, the not machine, and then the detector of one machine, okay? And I want to write down exactly what the composite is doing. And as we said earlier, this is going to be viewed as this, and then here, and this goes out, and this comes in. See, the not machine comes first, and that's very important, of course. And that's the outside box, okay? So using the formula I had before, I can write down exactly, and maybe I will write exactly, the input and output things, okay? So let me try and use algebra machinery, use the algebra machinery that really says you need to first take those two machines, take their product, so take the laxator, so start, yeah, let me just rewrite this to make this clearer. So start from something here and something here. Then you apply the laxator of DDS, the laxator on AA, and the laxator is going to get you to DDS of A times A and A times A. And then you're going to apply DDS, our function, to that specific wiring arrangement, which is exactly the one I kept on board here. This is the serial composition of phi, the serial composition. And it goes to DDS of A. Okay, it comes from A, goes from A. So let me try and write them down. Maybe they're going to be illuminating, maybe not. The output is always easier. So the output goes from AB times RST, because remember, these are the states of the two things, you just have to make them go together. And then you have to do F readout times G readout, and go all the way to AA. And then just do pi to A. Yeah, maybe this is not going to be illuminating at this point. This is how the machinery works. And for each specific thing, so let me do an example. Take A and R. The readout of each one of them separately is going to give me a 0 for A and a 0 for R. Maybe I'm using dumb examples. And that gets you all the way to 0. Okay? So that is the output of this composed machine here. And the input is going to be a very long composite, which maybe I don't want to write down. Should I write it down? Somebody has an opinion? I'll take it on me. A, B, R, S, T. So the first thing we're supposed to do, let me just, I don't need them anymore. The first thing we're supposed to do is duplicate the states. It's going to be 1 delta. So you see already that that's going to be huge. We're duplicating them. All right, now we have the same state twice for both the machines. So I have this information, and I will use them to actually produce an output. I want to produce an output and use it because of this feedback loop. Okay? So on this part of the data, I'm going to apply this function here, the output function. So I'm all the way to A times A times A. So these two things give me certain outputs. These two things. And this is F readout times G readout. So that is just great. I have a bunch of outputs here from my states, the states I started with. And then at the very end, before I go to the very end, I'm applying this phi1. This is the part that actually gets me to those things that I want to use. Not all three things are relevant. This wire, and this wire, I need to keep the first true and throw the other out. So this is really pi 1, 2. So keeping these two first information, and then it's the end. Because then I'm using the two informations I kept, and I'm applying them to the states I kept from before, and go all the way by F update and G update to AB and RST. Okay, I route the big composite down, but this doesn't tell me right away what I'm supposed to do with a series of inputs, and now I'm going to apply a series of inputs. I'm going to start from AR, my initial states, and I'm going to apply the following series. 0, I'm not telling you what's going to happen yet. We're going to figure this out together, at least at the beginning. 1, then 1, then 0, then 0, and that's it. Oh, let me do one more. 1. So we're going to do this series of inputs and see what the output is. First of all, before I do it, just by thinking of this serial composition of the two systems, do you think you know the answer already? So first, I'm changing every 0 to a 1 and every 1 to a 0, and then I'm doing the 1, 1 detector. What do you think the composite should be?
0, 0 detector.
The 0, 0 detector. That's great, but with a twist. It's going to detect the 0, 0s, and you're going to see that after these two zeros, you're going to see a 1, but because of the internal loop, and every step of this process takes 1 clock tick. 1 clock tick to enter, then 1 clock tick to output. The detector is going to happen 2 steps later. So we are going to get a 1, but only 2 steps after the 0, 0, which makes absolute sense if you think about the way those discrete and analytical systems work. This series creates a bit of a backlog in the inputs and the outputs here. This is 1 ahead, okay? So I thought that was interesting because at the beginning I was very confused why the 0, 0s don't give me a 1. They do give you a 1, but later. And this is very clear if you play with the states for a little bit. I don't know if I want to play with the states. Should we play with 1?
Yep.
Okay, so we start, A,
Yes.
R, and the input 0. Okay?
But we don't need to look at all that big, scary thing.
It's not scary, it's really what's happening though.
But I'd rather just look at these two machines somehow. Anyway, go
You
on.
can, but what if those, I agree with you, but what if those two machines are not easy to think about? I mean, yes, here you can think about what happens to them, but
Yeah.
what if like 5 machines? Like,
Uh-huh.
that's
Yeah.
why this is, yeah,
Yeah.
yeah, I agree.
Right, but
But-
first, okay.
Yeah.
Do it however we want.
Okay, let me do just one using the formula and then we can think about the rest. So this first thing just duplicates the two inputs, the two states, AR, AR. Then those two firsts will output something. And I have 0 here, and A outputs 0, and R outputs 0. Do you see? Over there. It outputs 0. So these are the outputs of the inputs I chose. And I still keep the AR around. Then this projection says, you know what? The third one you kept is irrelevant to me right now because I'm only feeding this back, and this is coming from the outside world. So this is 0, 0, AR. And then it says 0 and A. What does 0 and A do? What does 0 and A do? Go to B. You see? 0 and A go to B. So this goes to B. And where does R and 0 go? R and 0 go to R. This is going to be BR. And you can go all the way doing this, but you're never going to reach T, because if you look at this, only T gives you the indication. Only T has 1 as output, but you're never going to reach T unless you actually do these 2 zeros in a row, wait 1, and then the 1 is going to come out here as an output. So that is the idea. And I agree, you can think about them and go, I don't know how easy it is. Maybe, I hadn't thought of doing it on my own. Like where do I go after BR?
Let's see, so if I'm at BR and you give me a 1,
Mm-hmm.
then the B hops over to an A,
Mm-hmm.
and then what it does, it spits out a, sorry, it spits out something, a number that feeds to the other machine.
One.
It spits out a
It
1,
feeds a
that's
one.
where the number, and then that 1 meets the R
Yes.
and gives you an S.
Exactly. Yeah,
Yeah,
that's the
uh-huh,
idea.
yeah,
Yeah,
uh-huh.
that's how you go about
Right,
it.
yeah.
Precisely. So it is a 0, 0 indicator with 1 moment lapse.
Uh-huh.
So let me just, sorry?
They said I see.
You see? Let me just finish off with a high-level observation. I mean, these are all very fun and nice to work with. But as I said at the very beginning, there was this idea of actually, like, you don't want to only compose Moore machines with Moore machines, right? Sometimes. I mean, the systems in the real world are much more complex than that. And also, you may have a Moore machine, but maybe then you have a human being, which you want to monitor their behavior, and you can't actually. But anyway, because it's really unpredictable. What I'm trying to say is that the bottom line is that you want to try and also compose things that are not of the same algebra type. okay? And in our latest paper with David and Patrick, which is called Dynamical Systems and Shifts, we created new algebras that are very high power. So we created an algebra called machines, yes? Discrete machines, because I need to remember that there's a discrete time situation going there. Also, they're total and deterministic, which I would love to talk about, but clearly Moore machines are total and deterministic. Deterministic because given any input and state, you know what's going to come out because of these two functions, and total just means that any input it gets is going to output something, because there are some machines that you don't know whether they're going to have an output or not. They're not going to run necessarily. So anyway, there is this big algebra that it's really a span algebra. It's really a span algebra. Objects in this algebra, the categories, are span-like things, which is not the first time that people use spans to actually model systems, okay? And this goes all the way to CAT. Then I had my Moore machine here, so discrete dynamical systems that we described earlier. Then this has some input wires that are not just sets, but in a sense, they are lists of sets, and they employ a sheaf theoretic ideas of natural numbers. So for every natural number, you have a sheaf of possible things that can go through the wire, okay? And by the functor I described a little bit earlier, for no apparent reason at the time, there is an inclusion here. So this means that this is a subalgebra of this, meaning every time I have a Moore machine here, if I want to actually find a more broad framework in which I can connect it to other broad machines, not necessarily Moore machines, I can translate every discrete dynamical systems in one of those spans and then go and connect it to other spans around it. So it gives you a freedom, it gives you a more higher level framework in which to work with systems that are subsystems in a specific monoidal way of this more general idea of system. I think that would be all.
So this broader world is supposed to include all total deterministic
Systems.
machines, and there's still some kind of discrete time.
Yeah, there is some discrete timing, which is very important, because one of the major goals back when we were at MIT was to wire together more machines with continuous dynamical systems. And continuous dynamical systems have differential equations, and they run in continuous time. There's no way, there are ways, but they have to also live in the same time to talk to one another. So there is yet another machine, which is called synchronous time, that actually both the discrete and the continuous machines talk together. They are subalgebras of this big. And that's where actually Moore machines and continuous dynamical systems can be wired. And you can say something about their output compositionally.
Sorry, do you embed the discrete into continuous or vice versa?
That's what you would expect, which is very surprising, right? But they do not embed to neither. They map to a new one, the synchronous one. So the synchronous one has sheaves, but they're continuous, but with a chosen phase. You have to say where you're starting somehow. And that's where they start talking to one another. It's really very elaborate. I mean, mathematically it makes sense, but if you start thinking about what it means, it becomes really powerful. Yeah, it's not as straightforward. Yeah.
So this DDS functor was picking out boxes of certain shape.
Exactly.
Right? What made a discrete dynamical or a Moore machine was just that you had this intermediary state set that input and output in a certain way.
Yes.
Are a lot of the main types of functors just picking out special kinds of shapes that
Yes.
are doing a certain?
Yes, exactly. I mean, the state is very important to a system, clearly, but even for these uber general machines, picking out an inhabitant of the box, well, now the input and output are not sets, but they're these discrete sheaves, whatever. It's really picking another sheaf, another discrete sheaf, and then having maps like that. That's really what it is, as simple as that. It's like picking a state and then input and output that realize them to the outside world. This is common, I would say. I don't know if it's for every system. I would love to know, I would love to work on many more examples than that, but it looks like there's a common pattern there, yeah. Yeah.
So all of this is very, the very classical logic, duplicate and throw away signals. So is there a model that anyone's thinking about for more like linear logic-y type of system?
So I don't know what linear logic is,
It's
but
like
do
you can't duplicate, you can't throw things away.
you're saying
If you had
changing
quantum machines, you would not be allowed
to do stuff
to
like that?
duplicate.
So you want
Yeah,
a typing category that it's not necessarily finitely complete in a
Yeah,
sense.
so it'd be probably
Just
more like
monoidal.
Hilbert space than rather than set, I guess.
Yeah, some sort of,
So sort of-
symmetric monoidal rather than,
That's a good question.
Cartesian.
Myself not, but David and Patrick worked on those machines and a lot of logic afterwards later. And they have this book now that has to do with logic and those machines. But I thought that their typing categories were still finite product. Maybe I'm mistaken actually. I can show you later where we can look together to see if this changed in some way.
You get rid of duplication and deletion, and then you can't do all of the line and line.
The feedback
Yeah,
and
change a lot.
things like that. Suspicious.
but people are, theoretically, they talk about like quantum circuits, and
Mhm.
sticking together quantum circuits, to form bigger quantum circuits. So there should be some sort of language that can
Capture that.
handle those. So it's a little strange. Because those pictures look like pictures that you could draw this way.
But they're not
But
really.
it seems like maybe somehow they don't quite fit in this framework. I'm not sure. Yeah.
Okay, me neither, but that's a good point.
Or? No, I guess
More
not.
machines?